So if we keep going, talking about frames and machines, if we go back to page 1, we introduced this concept of machines. Any structure that contains parts which alter or transmit the effects of forces. And again, ropes and cables are only going to hold tension, and it's the same tension at all points in that rope or cable. So we're going to employ that here. And also, pulleys are assumed to be frictionless. So we're going to employ those two concepts for. Got a nice example here. You can see it before I draw it here. So we've got this frame that's got a pulley out here on D, an 800-pound weight attached to it. That rope we've got a rope or a cable coming across that pulley here, and then attaches in this member BC over here. So let's I'll draw this with you. So 2 pins on this one supporting this structure. I've got a pin example here. Got a pin all the way over here at A on the left. Some sort of member. It's long. It says it's 68 inches total. 30 inches out to where member BC attaches, and then another 38 out to where the pulley attaches. So attach with the pin over here on point A on the left. And then again, member BC then goes straight up and attaches to a pin up here. So it's a vertical member. So B being this pin up at the top, C being this pin right in the middle of this member, starting with A on the left. And then over here, I've got another pin, and on this end, I've got a pulley. So we might draw it similar to how I would normally draw a roller, but it's actually just a pulley, meaning it's just a wheel out there, kind of like a roller. And then I've got a cable then going across that pulley. And then that cable comes straight out horizontally from that pulley until it reaches an attachment over here on this member BC. So maybe a loop around that member BC, or somehow through a hole or something. Somehow it's attached to BC and it's pulling horizontally right there on BC. The other end of this rope is attached to an 800-pound load. So essentially this is some type of a simple crane structure. And what we want to know, this one's pretty straightforward. It just says find the reactions at A and B. So it wants to know, and it's going to want to know horizontal and vertical. At this point, not very often are we going to worry too much about the magnitude and direction on forces like that. We want to know what are the horizontal and vertical components. That's going to be what's helpful at this point. All right, so how do we do that? Well, we could draw free body diagram of the whole structure. And I've got 800 pounds acting out here. I've got BX there, and I've got BX and BY here, and I've got AX and AY. And one might say, wait, Steve, is this a two-force member? No, it's not, because this cable's attached right here, so I don't just have pins on either end. Same thing with this member AC, and the pulley is at point D. So this is not a two-force member here either, because I've got forces applied in the middle of it, or not really in the middle, just a certain distance. So let's mark distances here. 30 inches horizontally between A and C, another 30 inches out, 38 inches. 38 inches out to where, from C to the pin connection at D is what that's pointing to. Dot that a little bit darker for you there. All right, so not to the 800-pound force. I've drawn that very poorly. All the way out to this pin right here on point D. That's going to be important in just a second. Vertically between point C and this cable attachment is going to be 8 inches, and then another 14 inches up to that pin where the cable attaches up to the pin at point B. 14 inches there. Okay. So as I was saying earlier, you could draw a free body diagram of the whole thing, and you would have unknowns here and here. Realistically, we really should take this pulley off at D if I were to do that, but then I would have also unknowns at point D. But the thing is, those knowns, those D forces on that pin at D are actually pretty easy to find. Let's start there. Sometimes when you get a pulley, it just makes sense to go ahead and look at it. Let's remove basically all the cables and ropes, and let's see what that looks like. So if I just look at this pulley D, okay, pulley D. Now I have, because I've taken a pin apart, I'm going to draw dx and dy, and I'm going to draw those in the positive direction because this is the first time I'm drawing those on a free body diagram. That's my method. You don't have to follow that, but that is my method. Is to, one less thing I have to keep track of is what sign am I using there. I like to draw those pin reactions positive the first time I draw them. What else is attached here at D? Well, I've got an 800-pound load coming down on this cable here, and remember we said that it's the same, if I go back to page 1, same tension at all points of the rope or cable. So it's the same cable all the way through here, meaning this 800 pounds being applied right here is the same 800 pounds applied all the way through. So everywhere I remove this cable or rope on a free body diagram, I need to draw an 800-pound pulling force. So I've removed it here, but it also comes off right here. So I also have an 800-pound tension pulling on it in that horizontal direction of this cable here. So I have 800 pounds pulling in the direction of that cable. So that's not too bad. I should just need two equations for this. Sum of forces in the x direction, I've got d that's equal to 0. That means 0 is equal to dx minus 800 pounds. dx is equal to 800 pounds. That's easy. Okay. Sum of forces in the y direction equal to 0. That's, I've drawn dy positive and 800 pounds negative. So 0 is equal to dy minus 800 pounds. That's just simply dy is equal to 800 pounds. Easy enough. All right. One free body diagram, two unknowns, two equations, two unknowns. Go. All right. Now, what might we do? What are we looking for? We'll go back to basic problem solving. What am I looking for? I'm looking for reactions at point A and B. Okay. Well, I know I've got two unknowns here and I've got two unknowns there. I've got AX, AY, BX, BY. So I'm going to need at least a couple free body diagrams. Now, why did I do this? Well, because I got these cables here, and I want to know what else is going on with those cables. You didn't necessarily have to do this step first. You could have just as easily drawn, we could draw about anything. And I'm going to do this problem kind of in weird order, not your traditional order, because I just want you to see that you don't have to go find your reactions first, and then find this, and then find that. You're welcome to kind of move around this thing a little bit. You do want to be pretty systematic. If I could have found the reactions here and there in one free body diagram, I would have already done it. But I know I've got four unknowns here. So one free body diagram is not going to get me, so I'm going to have to piece this thing together. So there's really not a right or wrong free body diagram to draw next. I'm going to tell you what I'm going to do just because of experience. Experience tells me if I draw, now that I know dx and dy here, right? Now I know dx and dy here, if I draw this member here from A to D, take all the other pins apart, I can't solve it, but I can get some unknowns, at least one unknown out of that. And that's really all I need at this point, is just one more unknown, and then I could look at a free body diagram of the whole thing. So let's do that. Let's look at free body diagram of A, C, D. And again, you don't have to do it exactly as I'm doing it here. As long as you kind of apply a nice systematic approach and you don't violate any algebra rules, there's not a lot of wrong, well, there are a lot of wrong ways to do this, but there's a lot of right ways to do this. All right, so I'm drawing a free body diagram of ACD here. Okay, now I've taken apart pins at point A, This is the first side I'm seeing of A, so I'm going to draw it AX and AY. I'm going to draw both of them positive because I don't know them. Same thing at C. I've taken a pin apart at C, so I'm going to draw CY and CX. Now, you can do this a couple of ways. Notice this is one side of this pin. This is the other. Right? There's two sides of this pin. There's the side that's acting on the pulley, and there's the side acting on this guy. And when you put them together, you want them to cancel out. So since I've drawn both of these positive, I'm going to draw both of these negative. This is the other side of the pin. If I've drawn one side positive, I'm going to draw the other side negative. Notice I found both of these to have a positive value. If I found either one of these to have a negative value and I've drawn them positive here and I realize it's actually negative, then I have a choice. Either I can draw it in the opposite on this side, or I can do as I've done it here and say, well, you know what? I'm going to draw it positive here. I'm going to draw it negative there. Whatever sign these guys pick up, I'm just going to plug that sign into the equation along with the sign that gets drawn on the free body diagram. But again, when I put these two together, these need to be equal and opposite. They need to cancel out. So I'm drawing them one direction on one free body diagram, drawing them the other direction on the other one. Okay, so I know dx and dy. Those are known. dx equal to 800 pounds. dy equal to 800 pounds. Those are known. I also know distances here. I know this is 30 inches. If I use a moment equation, that's going to be important. And this one's 38 inches. Now, as I said, I can't solve for all four of these unknowns from this one free body diagram. I've got 6 parameters. I know 2 of them. I can only write 3 equations, so I can only solve for up to 3 of these on this free body diagram. But, excuse me, what I can do is this. I can say, well, I don't care about CX and CY. All I really care about is AX and AY. So if I don't care about CX and CY, what if I take my sum of moments about C and set that equal to 0? And only look at the forces causing a moment about C. Well, notice AX passes through point C and DX passes through point C. The only 2 forces causing a moment about point C are going to be dy and AY. So I'm going to draw, let's see, no. Well, they're both negative, so it doesn't matter. So I'm going to say minus AY, because they're both causing a clockwise motion about point C as I've drawn them here. So minus AY, and that's at a distance of 30 inches from point C. And also causing a clockwise motion about point C is dy. So it's minus dy. And its distance is 38 inches. So when you solve this, this is 0 is equal to these things. When you solve this, you find that AY, I have written down here is minus 1,013 pounds. So I've drawn it positive here. It actually picks up a negative sign. Now, can I find anything else? Sure, I could find CY if I wanted to. That's okay. I could find CY right now. Right? Notice sum of forces in the y direction equals 0. Equals, I've drawn AY positive minus dy plus CY. And I found AY as a negative value. I know dy. So that, if I'm looking at this right, that means then CY would sum to be the sum of those two, 1,813 pounds. So I could do that. Now, I can't find these x values though, because I can only write one more equation. What I can do is I can put AX in terms of CX. Right, maybe that's not the worst thing to do. Sum of forces in the x direction equal to 0. I could say ax plus cx minus dx. That's all equal to 0. So what that means is that cx plus ax are going to have to add up to be 800 pounds, the value of dx. Okay. So again, I can't solve for either of these. I can only write 3 equations from one free body diagram, but I can put them in terms of each other. So that gives me another equation. So what I can do then, I can do one of 2 things. Right? Now, I was kind of having an internal dialogue in my head I didn't talk about. The solution I've got worked out on my notes here then goes through and draws this attached to ACD, and I'm thinking, well, you know, that's a nice way to do it. Maybe we look at that solution, but I think let's do this. Let's just draw a free body diagram of member BC now. So if we do that, we draw a free body diagram of member BC. Free body diagram of BC. I've got a pen up here at B. I'm going to draw it as BX and BY. I've got 800 pounds kind of attached halfway out. It's not really halfway down. It's actually 14 inches from the top. If you look back at the original diagram, and then it's 8 inches down to point C. Now again, remember I drew CX and CY positive here, both positive here. I found CY to be a positive 1813 pounds, and CX is unknown. But again, I drew those positive on that diagram, so I'm going to draw them now negative. I'm going to draw the opposite of those, because I'm looking at the other side now of this pin. And so if I write equations here, well, what equations should we write? I could write sum of forces in the y direction. That'd be easy. Sum of forces in the y direction, that is by minus cy, is going to add up to be 0, and I have a value for cy. Back over here, 1813 pounds. So that tells me by is equal to cy, which is 1,813 pounds. Known value. So that's one of our answers we're looking for. We've already found, by the way, we've already found one of our other answers up here, this guy. Oh, sorry, you can't see that. This guy is an answer. Because what are we looking for? We're looking for reactions at point A and B. Okay, what do we have? Well, we got to do some things to get to a point where we can find those. We found one of them. I still have more equations than unknowns, so I need more equations. So let's draw a free body diagram of something else. That's where we're at. We're keep going through this problem-solving loop. Now I've got another answer. So now I know AY and BY. Now I got to get the X values. Okay. Well, I could write sum of forces in the X direction, and that would tell me this is equal to that. Notice I've got an equation back here relating if I can find CX, then I can use that to find AX. And I can relate now BX to CX, which relates BX to AX. But I need one more thing. Okay. Well, let's do this. Let's take our, again, sum of moments about point C. If I take sum of moments about point C, set that equal to 0. Let's write it down here. I can't get all of the terms in one line or in a half line there. Let's write them all out in one line. Sum of moments about point C are equal to 0. Okay, so I'm taking my moments about point C. These guys, no moments caused. BY, no moment caused. The only things causing moment are BX and this 800 pounds here. Okay. Well, as they're drawn, they're both causing a clockwise or negative moment. So minus 800 pounds at a distance of 8 inches. So clockwise 800 pounds at 8 inches. And then also I've got clockwise, about point C, I've got minus BX at a distance of 18 plus 4 is 22 inches. So I've written here Tell me if you're getting something different down in the comments. I'm written here that BX is about 291 pounds, and that's negative. I apologize. That is negative. It picks up a negative sign because, if I add this to over to the 0 side, then divide by 22. This is the value that I have written down as the answer. Now, how does that help us? Well, what am I looking for now? I was looking for the reactions at A and B. So I've got AY, I've got BY, and I've got now BX. I need AX. Okay, well I know AX in terms of CX, and I know BX, and I can write one more equation. I can say that the sum of forces now in the X direction are equal to 0, or I could take my moments about point B and find CX that way. Either way works. I know that BX, right now I've drawn it positive, so I'm going to add it in here. And I've drawn CX as negative, so BX minus CX are going to equal 0. So that means BX is equal to whatever CX is, or vice versa. I know CX plus AX is equal to 800 pounds. So what I'm going to do is I'm going to say, well, you know what? If CX plus AX is equal to 800 pounds, and I know BX is equal to CX, so that means BX plus AX is equal to 800 pounds. And I found a value for BX. BX, as I've gone through and drawn it systematically, if I carry a negative sign with it, it plugs into these equations because I solved it in this orientation. So BX, plug in a minus 291 here. So AX is going to equal 800 plus this 291. That's 1,091 pounds. Again, if it helps, feel free to write all your answers. We don't have to designate tension and compression here, so how do you draw which way it is? Because it reverses depending on which side of the pin you have. Well, that's why your free body diagrams are important. You need to make sure I understand what is. If you're going to give me this negative sign, make sure it's clear what does that mean, because in this case, for this side of the pin, it's just you're actually telling me it's going down here when we look at the whole thing. So AY is minus 1013 pounds. AX we just found to be 1,091 pounds. That disagrees with what I've written earlier. I'll pause and look at it here in just a second. Let's see, BX I found to be minus 291 pounds. And I found BY to be 1,813 pounds. Again, I'm going to consolidate with my notes here and see which one of these I like better. But that's what I have now. So I'm going to pause for a moment. All right, did you catch my error? Remember I said sum of forces in the X direction? Well, I've already shown it, right? I missed this 800 pounds. I said BX plus minus CX is equal to 0, and that was too easy, wasn't it? There's an 800 pound force there that I missed. Just being dumb. So BX is equal to CX minus 800 pounds, or really what I need is CX is equal to BX plus 800 pounds. CX is equal to BX plus 800 pounds. This is what I need because I remember from earlier CX plus AX is equal to 800 pounds. Now I know CX is BX plus 800 pounds, so BX plus 800 pounds plus AX is equal to 800 pounds. Just plug in for CX, BX plus 800 pounds. I've got 800 pounds on both sides of this equation. So AX plus BX is equal to 0, meaning AX is equal to a negative BX. I've already found BX is minus 291. That means AX is equal to a positive 291, the opposite of that, which jives then with what I've got in my notes over here. I went off script and I did the problem a different way. We did this, which we agree with. Take your sum moments about point C that gives you AY. Take AY then to this next free body diagram. So I said, well, you know what? Let's just draw both sides of this. my notes said, just draw the whole darn thing as one structure. I've got one value now is known. I now know AY is actually in the down direction, 1013.3 pounds. And now I've got 1, 2, 3 unknowns that I can solve. I can write equilibrium equations for this free body diagram and solve that out. And that's what I did here. So when I looked, I'm like, wait, I've got AX is 1091. Why do I have 291 over here? And I'm like, oh yeah, I missed this force. Took me a minute. That's what I get for going off script. Talking and writing and thinking about what I'm saying next. That gets kind of a, doesn't always work. Anyway, if you see something else, questions, comments, complaints, put them in the comments. This is now a 25-minute video, but I wanted to go ahead and get this all in one video, so I'm going to stop here.